So this video will just be on the continuation of the photoelectric effect. So just reminding you, this was our photoelectric effect where we were just shining light on a plate, really on the two plates of a capacitor, and we could vary the voltage, we could vary the intensity, we could even vary the frequency of this radiation, and we just plotted it out versus the current. And what we had shown is that the kinetic energy of these electrons does not depend on how bright this light is. No matter how bright this is, these do not come off any faster. We also said that these come off in almost no time right here. Even if this is a weak intensity, if you get light popping up, the electrons popping up, it doesn't take any time for that to happen. And the third was the kinetic energy does depend on the frequency. When you increase the frequency, you don't get more electrons. What you get is faster ones. And when you plotted it out, we got a curve like this right here. So it went up like this right here. And we said the slope of this line right here is equal to h, which is Planck's constant. Okay, and so we now, Einstein was the one that had solved this, and he did it in 1905, his miracle year. Within 3 months of doing all of his relativity work, he wrote 4 papers in 1905 within 4 months or so, and all 4 of them are deserving of a Nobel Prize. But this was another one right here, and he said, first of all, he said radiation, electromagnetic radiation is quantized. It's emitted and absorbed in units of HF. So he said light is, actually he's saying light is a particle with energy HF right here. So he says the energy of a photon is HF. Well, you notice this thing is really solving the Blackbody problem, because in Blackbody problem, remember we had these oscillating molecules on the walls of my cavity, and we said they could only oscillate at certain frequencies. That's because they could only emit photons of this frequency. So it wasn't that these things can only oscillate at certain frequencies, it's just that these things are emitting photons of light of this frequency. And you'll notice over here, the kinetic energy, or the energy, has nothing to do with the intensity of light. It only has to do with the frequency. So it only has to do with the frequency right there. Okay, so now what is he doing? He's saying now, okay, we have photons. I'll draw it like this. HF, photon coming in. What does it do? It has to, and then we get an electron popping off. Electron. But you have to free up the electron first. Electrons are bound into atoms. And so they give it this little symbol right there. They call it the work function. Or it's just a constant work function. It's how much energy it takes to free it out of the atom. And then the rest of the energy goes into kinetic. We don't have to use relativity. This is very low energy stuff, so we can just use our old kinetic, 1/2 mv squared. And this would be the maximum because that's where it's all going to. So we could just say it's the maximum kinetic energy, max. Okay, so there is that's all he said right here. HF, it seems so simple. I'll just rewrite it. 5 plus the kinetic energy max. Seems so simple, but even 10 years after he came up with this, even almost by 1915, they were saying, you know, that Einstein, he was a bright guy for relativity and some of this other stuff he did, but he was way off on this right here. This is way off. It wasn't, but by 1921 he got the Nobel Prize for this. So there was just so much evidence for it. But I'm sure this puzzled Einstein right here. He's probably thinking, I'm opening up a can of worms. I can see some spooky stuff coming up in the future because of this right here. I'm sure he must have thought about this spookiness right here. But what do you mean by spookiness? Well, suppose you have a light source right here, and you have some glass right here, and embedded in the glass, I have a detector that can detect these photons. They detect them one at a time. Photons. This is just a detector. Okay, lights come down. Some of them, when they hit the surface of the glass, get reflected right here. Some of them go on through. You can calculate about 4% get reflected and about 96% coming down here. So this thing would detect about 96% of the photons coming in. And let's say you put another detector right there, put a little guard so you don't get it straight across, and you get about 4% bouncing back. Okay? But now, suppose I don't embed this in glass. Suppose I just have a pane of glass here. I have a pane of glass. I'll put it below the pane of glass. And here's my source of photons coming down. And I'll put a barrier here and put my detector right here to get the ones that are bouncing back up. Okay, so now you'd think, well, I got 4% coming off of there, and then some comes down to here. Again, I would expect some to bounce off from this one too. So I would expect maybe more than 4% in this one. I would expect more than 4%, at least 4%, and I would expect, well, that would mean I'd need less than 96% down here, not less than 96%. But if you do this, you don't get, what you get bouncing off is you get anywhere from 0 to, I think 16% or so. How could you get 0? You're already getting the 4% just from that top surface, just like you got it from here. How could you possibly get 0 if you just have it? What determines whether it's 0 to 16 is the thickness. You have a certain thickness, you're going to get 0. If you have a different thickness, you could get 10%, another one 16. It's going to vary right there. So it all depends on this thickness. Well, when this photon is coming down, how does he know how thick it is before he even gets there? He has to know, because if it's a certain thickness, I don't want to bounce off. And so there's only one way he can know how thick it is he has to send out a scout ahead of himself to look. Say, what's the thickness? Okay, it's just thick enough, don't bounce off right here. Not only that, what if we had 5 panes of glass here? Well, what gets up here depends on the thickness of all those panes of glass. So that means this scout has to go and check them all out and then come back and say, okay, now we'll tell you what to do. And so this is what I mean by spookiness right here, that Einstein was probably thinking about not long after he came up with this right here. So you'll notice, if we come back to this thing right here, what are we plotting? We're plotting out the maximum kinetic versus the frequency. If I just solve for the maximum kinetic, what do we get here? I'll just move this over to the other side. Kinetic energy max is equal to HF minus phi. Well, this looks like a straight line. This looks like y equals mx plus b. X was my frequency, y was my kinetic max. You can see right here, what's the slope? The slope is h, and the y-intercept is a negative my work function. So if I were to just continue this down right here, there's my y-intercept right there. That would have been the work function right there. The energy it takes just to free up the electron. Okay, but this is the formula. Nice simple formula for photoelectric effect. So let's look at an example right here. Suppose you're given light shining at it. I'll give it in terms of wavelength. Let's just say the wavelength hitting it is 400 nanometers. 400 nanometers is in the ultraviolet part of the spectrum. Usually this is happening in the ultraviolet part. Infrared doesn't have enough energy to kick off electrons. Ultraviolet does. You probably even notice the photoelectric effect sometimes when you walk into like a 7-Eleven store. As soon as you pass a beam of light, you get a little bell going on right here. And that's what they're doing. They're just looking at the photoelectric effect. As long as the beam is there, you're kicking off electrons and it makes a circuit. As soon as you get in front of it, you're stopping the beam and it rings the bell right there. Okay, and let's say we're on, this is for lithium. For lithium, actually let me write that a little bit better. For lithium, the work function for lithium is 2.9. Phi is equal to 2.9 eV. And so my first question is, what's the photon energy? There's the wavelength. We know the photon has an energy of HF, but we are giving it to us in terms of wavelength, so we'll turn this into C over the wavelength. So this is HC over the wavelength. Now, H and C a lot of times pop up together. If you combine those two constants, it's a nice constant to have. It's 1.240 times 10 to the 3 eV nanometers. You might write that down in your book if it's not in the back of the book right there. It's just a nice constant, H with C put together. So if I put that up into here, I get 1.24 times 10 to the 3 eV nanometers divided by the wavelength, which is 400 nanometers. Well, nanometers drop out, and I'm just in eV, which is what I should be. It's an energy. This is 1,240 divided by 400, which is a little bit more than 3. This is like 3.1 eV. So that's the energy of the photon right there. Now they asked, what is the stopping voltage right here? Well, when we said this before, the stopping voltage was, we said that EV naught was the maximum kinetic energy. So we said that was the voltage it took to stop all these right here. Well, what do we say kinetic energy max is? It's right here. It's HF minus phi. So this is HF minus phi. But we know what HF is. It's right here. It's 3.1 eV minus phi, which is 2.9 eV, which is 0.2 eV. But that's the kinetic energy. If we just wanted to get the voltage, V naught, we can just cancel the E's. That's just 0.2 volts. So there's the stopping voltage. Okay, and then another question is suppose you wanted to produce you wanted these guys to be 3 eV. What frequency do I have to put in? So I'm not putting in 400 nanometers anymore, but what frequency do I have to put in so that this is 3 eV? So I want this to be 3 eV. And this I know right here. And so we got HF equals is equal to the phi, which we said was 2.9, plus the kinetic, and they wanted the kinetic to be 3 eV, so we'll just add 3. So this is going to have to be 5.9 eV. I'm going to have to shine 5.9 MeV photons to make it. But they wanted the frequency, so I have to divide out the H. So this is 5.9. And now we'd like to put H, when we wrote H before, we wrote it in joule seconds, but we can also put it in eV seconds. H is also 4.136 times 10 to the minus 15 eV seconds. H has units of energy times seconds. Okay, so we can just put that down below here. 4.136 times 10 to the minus 15 eV seconds. The EVs drop out, and you just get seconds in the denominator, which is just a hertz. And so that's going to end up being, this is a little bit more than 1, and that's going to be the times 10 to the plus 15. So this is, it's actually 1.4 times 10 to the 15 hertz. Okay, so any of these questions on the homework with the photoelectric effect, it's pretty much all you're going to do, where this is E times the stopping voltage, this term right there. Okay. What about the reverse process of the photoelectric? Anything that can happen one way, you can run it backwards right here. So what would be the reverse process? The reverse process is you throw electrons at it, and out pop photons. Right there, you get HF, whatever, HF's coming out right here. Okay, they don't call it the inverse photoelectric effect. They actually give it a name. It's a German name. They call it Bremsstrahlung. B-R-E-M Strahlung. Big name right here. Okay, and how could we make Bremsstrahlung radiation? That's the photons coming out right there. Well, let's come back to our parallel plates. Hook it back up to our battery. Except I'm going to make this battery much larger right here. These voltages weren't that big right here, a couple of volts. I'm going to move this voltage, let's say up to 40,000 volts. Right here. And you've got so many electrons here that are piling up there that they don't want to be there anymore, and you're going to just kick them across right here. Now I'm going to take the air out of here so they don't run into air. So we'll take the air out, make that a vacuum. But there's such a high, they're picking up a lot of speed coming across. And before they hit the end, I'm going to put a target right there, a piece of metal. Could be tungsten or chromium or some other material right there. And so this thing's going to go, these are my fast electrons. They go slamming into this material. They make the photons coming out, the HF right here. This is the way they make the x-rays at your dentist's office or at any doctor's office. They just need a high voltage to get a beam of electrons. Why? They need that huge acceleration, and when you run into a wall, that's a huge acceleration, and you can get out x-rays. And we could say that all of this energy, this kinetic energy of the or the energy of going from here to here is the kinetic energy, which is EV naught, right here, the voltage across there. That's equal to the energy of the photon, which is HF, which is hc over wavelength, and if you just wanted to solve for the wavelength that you're going to get, actually it's really the minimum wavelength because this is the maximum frequency right here you get. So the minimum wavelength you get is actually just hc, bring that over to here, take the EV down below, so it's all over EV naught. So if I crank up the voltage, I can look at smaller wavelength, higher energy. So if you're gonna, the dentist's office, they're not looking through thick material, just through your gums and stuff, lips. But if you want to look through a leg or something, you're gonna have to crank this voltage up a little bit more so you get a smaller wavelength, more penetrating. And if you looked at the intensity, you know, for a certain like tungsten, it would go like that. This is wavelength and this would be the minimum. All different materials, as long as they're at the same voltage, would all go to the same spot right there. And this is the intensity. Okay, now here, remember, the photoelectric effect is a photon coming in, an electron popping off. That's the photoelectric effect. Can that happen to just a free electron in space? Suppose you have an electron in space right there. Can a photon come in, HF, absorb, because that's what that did, and afterwards this thing is popping off at some speed? Right there. Can that happen? Well, let's just see. If I can get a solution and conserve both energy and momentum, then it can happen. Well, let's look at the momentum. We'll even use relativity, right? Might as well. What was the momentum equation? Well, before, we just have the momentum of this right here. So we just have the momentum of the gamma. This one is not moving, so he has no momentum. And then afterwards, all we have is that. That's the momentum of the electron. Since they're both equal, heck, why don't I just call them both P? Since they're both the same, I don't need subscripts. Okay, so now let's look at the energy. Well, this has no mass, so we know E is just PC. I could write P gamma C, but we know both P's are the same, so I can just say PC. This thing has no velocity or no momentum, so all of his energy is just mc squared, plus m sub bc squared. Okay, there's the energy before. The energy afterwards, it's the square root of the momentum, P. Doesn't matter if I say PE because they're both the same, P squared, C squared, plus the mass of the electron squared, C to the fourth. So that would be my energy equation. But I can see if I were to square both sides here, this would not be equal. Because if I square this, I just get these two terms. If I square this, I get these two squared, plus I got the middle term. So energy cannot be conserved in this collision process. So this can never happen. Never happen. Oh wait, what's going to happen? If that doesn't, something's got to happen right here. But not only that, if we were to plot out, this is the energy going along this way, energy. And this is the probability of what happens. Probability of occurrence. Well, the photoelectric effect at very low energies, it happens all the time. But, you know, even when you're within an atom, here's an electron in an atom right here, these electrons are only held in by a few eV. What if this energy right here has got 1,000,000 eV? Well, then that's pretty much free right here. He doesn't notice it. So at super high energies, the electrons even in the atom start to appear free just because you're talking about so much energy. So what that means is that the probability of occurrence drops right here. This is the probability of occurrence for the photoelectric effect. Photoelectric effect. So at high energies, as you crank up the energies, you're not going to get as much photoelectric events right here. They're just harder to happen because the electrons are hardly held in by the atom when you have super high energy. That means something else is going to take over right here. There's something else that's going to start, some other process that's going to start growing right here. And we'll talk about that on the next one. This is called the Compton process. And this crossover point is kind of depends on the material right here. If you're talking about lead, it'll probably be, high on the periodic table, it's probably going to be moved that way a little bit, lead. And if you're talking about something low on the period, like silicon or something, low on the periodic table, it's probably going to be over more this way, right, the crossover. But this is now a different process that's going to slowly take over when you start to go up to higher energies. And we'll get into this process on the next lecture. Okay.